Hello there. Um, so I've been wanting to make a video like this for a while. Um, so as this text says, the focus of this video is making a demonstration of using buffers for accessing data across various scopes of Max MSP. So like you can conveniently access a buffer in a lot of places in Max, in JavaScript, in Gen, in Jitter, and so on. So it's pretty convenient to use it as kind of a central database for more complex projects. Um, Sorry, I have a bit of a cold. Um, and yeah, so in this demo, I'm gonna build a simple synth controlled by a simple particle system, and I'll mainly be working in Gen codebox and Jitter GL. And yeah, I just want to do this because I use this method a lot in a lot of my devices. Not just in the exact way I'm doing it here, but I'll use buffers a lot. I can't say I've done tons of like benchmark and tell you if this is the most efficient way to do things, but for me it's been very clean, readable, and yeah, often it's very efficient. I think the thing we'll make today is very low CPU. Um, yeah, okay, so let's dive into it. I'm just gonna delete this. Okay, so um, the first thing I'm gonna do is do a load mass 8, and this number 8 is going to be the number of particles. So in this simple demo, we're just going to have a fixed number of particles. Obviously, some things will have to change a little if you want to make it dynamic. So this is number of particles. Okay, and then we're going to want our buffer. This is what everything's going to be accessing to visualize the particles and use them in DSP. Sorry, I don't have a pop filter. So we'll just call this, sorry, we'll just call this buffer particles. Okay, so there's various ways you can go about doing this. So this is a little bit of an advanced intermediate demo, so I'm not going to be explaining everything that I'll explain what I can, but not, everything. So hopefully you know a bit about buffers and stuff in general. Okay, so first we start with the name. And then the next argument is like the size in milliseconds. We're going to size it in samples, so I'll just do a 1 for now. And then it's the number of channels. So you can set this up however you want. How I usually do it, although I don't always do it this way, is that I do the number of channels is like the number of parameters. And the number of samples is the number of instances. So if you're a little confused, I'll explain that a bit more. So right now, I'm just going to type some stuff and explain it. So I'm going to do 4 channels, and then we're going to size this with this number of particles. So to size a buffer in samples, we use the size in samps instead of the normal size function. And let's just hook those up. And I'll double click it to send it in. So now it should be sized to 8 samples. So we have 8 samples and we have 4 channels. So there's 8 particles. So we have 8 samples, 8 slots here, and each particle has 4 parameters. So what are those 4 parameters? Why did I do that? Well, I'll tell you. And I'll write a note here for later. So here's the channel info, which is also the parameter info, or however you want to name that. Okay, so channel 0 or 1, we're going to do 0 based because in Gen and in OpenGL, or at least in Gen, channels are 0 based. Now, if you used peek poke and other objects in other places, the channel will be 1 based, which means the first channel starts at 1. But for Gen, the first channel starts at 0. So channel 0 is going to be the X position of the particle. Channel 1 is going to be the Y position. Channel 2 is going to be the X velocity. And that's like the distance or step distance that the particle will move each frame. So it's like, yeah, hopefully you know a bit about velocity. And y, and the fourth channel, or the third, is y velocity. So just to say, like, I'm not going to explain a bunch about like how particle physics work. Of course, I kind of will going through it, and this is a really simple system. There's not even a force vector, if you know what that means in this. But I encourage you to look more about that if you want to know more. Nature of Code by Daniel Schiffman is a great starting point. But yeah, so just to be clear, in this tutorial I won't go through details of everything because there's a lot involved in this. But I will try to explain stuff as best as I can. Okay, so, like, just to recap so far, we have 4 channels, and the reason we have 4 is because we want 4 parameters for every particle. And the parameters we want now are just x and y position and x and y velocity. Now, if you wanted to store a bunch more stuff, you just increase the number of channels here to like 8 or whatever. And many of my devices just have many more channels. It just depends. Okay, so we got the buffer set up, and that's going to be our main crux of everything. All right, so now let's start with the gen code box. So I'll create a gen object and double click it to open. All right, and let's turn this plus into a code box. If you're not familiar with gen code box, I recommend watching or learning a bit about it. This could be a bit advanced for a first time, but you know, especially in text coding in general. But I'll try my best, of course, to explain. But just know there might be some gaps. So yeah, I'm just gonna erase what's here. But so essentially, there's gonna be 2 things that are gonna be done in this code box. The first thing is to run our particle simulation. So essentially, just move the particles around. The second aspect of this code box is to make sounds from the particles, or have the particles control some kind of simple synth. And I'll tell you what we're gonna do with this. So so for this particle simulation, what we're gonna do is we'll have 8 particles. The particles will be made or initialized with a random position and a random velocity, so like a random speed and position, essentially. And they'll move around until they hit the edges of the window that they're in. And once they hit an edge, they'll just get a new random position and velocity. So you'll just see a bunch of little circles or particles moving around until they hit the edge of the screen. And once they do, they'll get a new random position and velocity. And then that's the particle system, very simple. For the synth aspect, we're just going to do sine tone oscillators. And the okay, and every time a new particle is made, the sine tones will get a random, not just a random position and speed, but they're also going to get a random frequency and a random pitch or tuning. And then the x position that they're in will control the panning. So if they're more left, they'll pan more left. If they're more right, they'll pan more right. And then the y position will do a little bit of wavefolding just for fun. So the higher they are or lower they are, the higher they are, they'll have a higher wavefold. Okay, so I'm going to also re-explain that as I make it, but that gives you a little roadmap. So that's what this code box will program, and then in the Jitter OpenGL, we'll just visualize it. Now, you may ask yourself, why don't you just do everything in Jitter, and it's simpler, and then just have that control the sound? Well, you could do that, and the reason I'm not doing that is because I want to demonstrate how to do this in Gen to do other kinds of projects. You know, there's all kinds of stuff you can do. The other reason is that Jitter and stuff is Q limited. So even though, you know, matrix operations might be ideal, like in the OpenGL, you might like have issues with that. Like if the user moves their display, the sound might freeze or things like that. So it's good to do all this audio stuff in the DSP, So, okay, let's get started. Hang in there. It's going to be a good amount of stuff. So, we'll start by referencing our particles buffer. So, if you don't know, in Gen Codebox, you just make a buffer object with buffer, and particles is the name of our buffer right here. And you know, if you're confused by codebox and stuff, definitely look through it. If you just want to like review what the inlets and outlets of things do, you can just like here make the object. Buffer's not a good example, but if I did cycle, you know, I could see what inputs and outputs are expected from the object. There's also all sorts of other ways to learn about that. Anyway, so we got our reference to our buffer. Let's add some parameters. So parameters are just variables we can kind of set and access from outside of gen codebox and then also use it in the gen. So we can actually change this value from out here. So let's make a parameter just the number of particles, right? And I'll default that to 8, but just to, you know, make that redundant, or in case you want to just change it, let's set that from out here. So we load mess the number of particles, and we send that parameter into the gen. So you just have to write the number of the parameter name and the value, and that will set it. Okay. Now, okay. So we have the number of particles. We have the buffer. We're gonna need to initialize them. So I'm gonna make a history, which is just a value that's retained each frame. But please, these are just like quick pour descriptions. You'll have to learn about these basics maybe in a different tutorial. So I'm just gonna have a init parameter at 0, which lets it know that it hasn't been initialized. So let's give the particles some initial positions and velocities. So what we'll do is we'll check if it's not initialized with this conditional function. And if you don't know text coding, it's also probably good to learn it a bit. But yeah, this just gives us a condition. If it's not initialized, or if it's 0, and 0 is going to be a no. So like another clearer way to do it, I guess, is if it equals 0. Well, we're going to go through each particle and initialize it. So we're going to do a for loop. If you don't know for loops, you should probably look them up. But basically, we're going to just loop through the number of particles. And that's how you do the for loop. You can't do a plus plus, I assume, because it's not an integer data type. Okay. And that will go through each particle at a time. So loop through particles and initialize. Just these are comments, so these aren't code themselves, these little slash things. All right, so then we'll initialize them. Maybe I'm going to write a function, and you have to write functions above all this stuff. And that's because we're probably going to initialize, we're not just going to initialize them here, but remember, once the particle reaches the edge, it gets a new position, velocity, and frequency. So I'm just going to make a function called new particle. And you always have to return a value. I'm just going to return 0 because we don't actually need a value, but you have to return something always in the functions, otherwise they won't work. Okay. And what do we need? We're going to need to send it in our particles buffer. We're going to need the index, which is the I. And okay, so one thing we'll need is a scaling value for the velocity. And I'll describe that in a moment, but I'm just going to add that parameter now. So I'm just going to call it vel scalar. And I'm just going to start it at something low like that. Okay, I'll describe this more. Just accept it for now. And so if you don't know much about functions, hopefully you'll look those up, because this won't be a good tutorial on that. But this is just like something that we can call down here in the code. And hopefully it'll make more sense in a moment when I do it if you don't understand. So I'll fill this out in a second, but let's add it down here for now. So we're going to call, for each particle, we're going to call the new particle function. and we're going to send in the arguments. So this is our particles buffer, and it expects that up here. And the next one is I, which is our index up here. The namings don't have to match. It's just what makes sense, what's readable. And the veil scalar. So some of these are the same words. The index isn't. That's just how I'm doing it right now. You can do it, name it however you want. So yeah, so what's happening is every particle, we're calling this function to create a new particle. And we're sending in the array, or the buffer of the particles. We're sending in the index, and this scalar for the velocity, which I'll explain soon. All right, so we know that for our buffers particle, our particles buffer, that the 0 channel index is x, the 0 based, but the first channel is x, the second channel is y, the third channel is the velocity of x, and the fourth channel is the velocity of y. And hopefully you get that I said the first channel for 0 because it's the index starts at 0. Okay, so now that we've reiterated that, we can set these things. So what we can do is use the peek and poke functions to access and store data in the buffer. So what we'll do is write the buffer name, and we'll call the function .poke, because poke is storing, so we want to store something. The first argument of the poke function is the value that we want to store. So we just want to store a random value from -1 to 1, and perfectly noise function does that. It gives us a random value from -1 to 1. And then we'll store that in the index. So let me and 0. All right, so let me just explain that, and I'll show you with the poke out here. So maybe it's easier to read up here. So the first argument is, it says the value to write. The second one is the position to write it, or the index. So that's just the sample number. And then the third one is the channel to write it. So it's 0 based. I'm not sure what the fourth one is. Okay, interesting. So yeah, we'll just deal with those three. We can ignore the fourth. So yeah, so there we have the value to write, the sample index, and the channel, which is 0, which is x. So this is x. Just to reiterate, x is 0. I'm just going to copy this, paste it. All right, so we'll do the exact same thing, but for the next channel, which is y. So this just sets a random position for x and for y. Now we want to do the same thing with the velocity. We want a random velocity. And for velocity, you have two values. And again, I don't want to explain all of this because it'll take a lot of time. But basically, this is the direction it moves in, and you need an x direction and a y direction. And so we're getting a value between -1 and 1 for the velocity of x. So that means that it could move. If it's negative, it would be moving to the left. And if it's positive, it would be moving to the right, if you imagine a grid. But you can imagine, let's say it was 0.8. Then every frame, which we run a lot, it will move 0.8 steps. That's a huge step. It will fly off the screen in 2 steps or less. So we want it to be a lot lower. And here's where the velocity scalar comes in. We want to multiply the noise by that scalar, which is right now 0.001. So now the range of this can only be between, I'll write it. Range is going to be between -0.001 to positive 0.001. So now that's just a pretty small value. Again, if we change the velocity scalar value, it's going to change this range. Hopefully that makes sense. Okay, so let's just do the exact same thing. Oh, sorry, I have to increase this. So this is going to be 2 for the velocity x channel, and this will be 3 for the velocity y channel. Okay, so hopefully that makes sense. We've now, when we call this function, we're going through each particle, we're calling the function, and we're setting a random position here and a random velocity here for each particle. Okay, so that's how we initialized it. Now let's actually run the simulation and code that. So gen codebox, we're doing ~gen codebox. Test. Hello. Sorry, it was crackling from that. Okay, so we're using ~gen codebox, which runs at audio rate, which right now I think my sample rate is 44.1K. So this is for this many samples per second. So it runs this many times per second. That's pretty fast. We don't really need to run it that fast for a particle simulation. So instead, I'm gonna kind of downsample it or lower the frame rate, and I'll lower the frame rate here for the simulation, but not for the synth that comes later, because the synth itself we want to run at audio rate. So that means we need like a new frame, or we need to know when to trigger a new frame. So I'm gonna, sorry, it's getting messy. So I'm just gonna create this variable called new frame, and new frame is, there's a lot of ways you could do this. One way I like to do it is a bit funny. So I'm just gonna do, okay, I'll show you what I'm gonna do, and bear with me. So this XXX thing, it just means let's ignore that, and let's get the new frame, and I'll explain why I'm doing this in a moment. So I'm gonna make a counter object, and the first argument, and let's look, the first argument, if we create a counter, the first one is the amount to add per sample. So we want to count 1 time per sample. And then the second one is a non-zero value resets it. We don't want to reset it, so let's keep that at 0. And the third one is the limit. So this is this is kind of the count maximum. It's basically just counting to this number and going back to 0 over and over again, like a ramp. So basically this will be our frame rate in a sense, and let's just set it to 500. And what that means is that this is a ramp from 0 to 500 samples, and it'll count one times per sample. So that means that this is a loop that's 500 samples long, and at an audio rate of 44 times 1,000. I believe this is right. Okay, I think I did this right, which means this would be about 11 milliseconds long. Or if I'm wrong, it's pretty short. So we basically say, okay, wait. So this is a loop running 11 milliseconds, and then if we look at the output of the counter, the first one is the running total, so that's the current count, and the second one is the carry flag, so that's the flag, the trigger that it hit the count max. So this will be a 0, but the moment that it hits the maximum, it will be a 1 for that frame. So back to what I did here. When you do this kind of thing in gen codebox, this counter is actually returning 3 values, as we can see. So if we want to access all 3 values, we just to make it more clear, we do something like this. And this is just how it works. So if you do something like this, value 1 is going to be the running total, value 2 is going to be the carry flag, and value 3 is going to be the carry count or whatever. So back to what I did, XXX just means, I don't know, that's just to me, I've just made that to say ignore that. You could call it whatever you want. And then the next one is new frame, and that's because this is going to be a 1 every time that counter finishes. Now you can do this a lot of different ways, like with a phaser and detecting when it goes back to 0. It's essentially the same thing. I just feel like this is a little more efficient than that, because you don't have to do a delta thing, etc. So anyway, now we know Now we get, so if I make here, let's make, this is going to run the simulation. And we're going to run it with a condition. So if new frame, so that's essentially like saying if new frame equals 1. Because if it's 0, then it's not new frame. So maybe I'll just make it clear like this. But you don't have to put equals 0. You can just say if new frame. But I'll, since this, sorry, I'm getting audio dropouts. So since this is a tutorial, I'll just say equals 1, so it's just more clear. So yeah, hopefully that makes sense. We're just gonna be running everything in this code block every time new frame equals 1, which is roughly every 11 milliseconds or so, and we can increase that if we want. Okay, so that's our frame rate, and now we're gonna run the simulation. So I'm gonna copy this, because we're going to just want to loop through the particles again. So this is just us going through each particle again. Alright, so now we're going to run the actual particle simulation, which means we're going to move the particles around, and when they hit the wall, we're going to reset. We're going to reset their position and velocity. Alright, so, and I'm going to delete this comment because it's not always going to be true depending on the velocity scaling. Okay, so, yeah, what's the first thing we want to do? Well, the first thing we want to do is access these x, y, velocity x, and velocity y values. You know, you can do this in different ways. How I like to do it is just like how I'm going to do it now. So we'll say x equals, and then we're going to peak. So we had poke up here to store the value. Peak is we're going to get the value. So we're going to peak, and we're going to use the index I, because that's, remember, there's 8 samples for 8 particles. So it's going from 0 to 8, so, or 0 to 7, I guess, technically. And so we're going to peak the index, and then the next argument is the channel number. And remember that the first channel, 0, is x. So we're going to peak 0x. And let's just confirm that up here for you. Gotta give a fake name. So the first argument is the index to read. Second one is the channel offset, the channel. So yeah, that was just to clear that up for you. So yeah, here we get the x value. Now you don't necessarily have to do this because calling this also gives you x value, but it's a lot cleaner to do this, and it avoids continuously calling this function. Y, so I'm just going to copy this. So channel index 1 is y. All right, and then we need the velocities. So velocity x is 2, and oops, and velocity y is 3. So here now we have the x value. So we have the position and the velocity now. So I'll just write a comment, get values. All right, and then the next thing we want to do is get a new position based on velocity. Now, if you're doing other particle systems and stuff, right about here is where you probably get your force vector from. You know, like if you have gravity or wind or anything like that, you'll get your force. But we're not doing a force vector. We're going to have them move at a static random velocity until they hit the edge. So no force. So it's pretty simple. All we have to do is literally add the velocity to the position to get our new position. So, all right, get new position. So all we have to do is x is going to plus equal velocity x. So this, and if you don't know coding, this is the same as saying, I'll write it below. This is the same thing as saying x plus. So these two are identical. It's x equals x plus velocity x, but I'll keep the shorthand. All right, and then y plus equals vel y. So all we've done is we have the position x, and then we add the velocity or direction in x. And then we have the position y and add the velocity or direction y. So if x is positive, it'll move more to the right. If it's negative, it'll move to the left. And for y, if velocity y is positive, it'll move up. If velocity y is negative, it will move down. Great, so we have a new position. Now we need to check if it reach the edge of the screen, because the screen is only so big. Now, the screen boundary is -1 to 1. So the left boundary is -1 x, the right boundary is 1 x, bottom boundary is -1 y, top boundary is 1 y. Hopefully that makes sense. Oh gosh, sorry about these audio dropouts. Alright, so how do we check that? We can do it with a condition. So we'll just do kind of a long condition. So if x is less than -1, or if x is greater than 1, that means that the x has reached a boundary. Or if y is less than -1, or if y is greater than 1. So if any of these conditions are met, and this double logic thing, you probably should learn about logic elsewhere, but this is just saying or. And if any of these conditions are met, that means it's reached an edge. So what happens if it reaches an edge? Well, we want to create a new particle, just like I'm saying. We want to get a new random position and new random velocity. So we can just call this same new particle function. We don't have to write it again. So I just call new particle, pass in the particles buffer, the index, which is also I, the vel scalar, which is still called that. So it's exactly just like this. Great. Now, what if it doesn't reach the edge? Now you see, in this function, we're poking all these values to the buffer. But out here, we haven't poked to the buffer. Sure, we've peeked from it, but then we changed the position. So we gotta, if we didn't reach the edge, we gotta save this new position in the buffer. So, save new position. So I'll write else, and this else is related to this if, because if it's reached the edge, we already store it, so we don't need to do this. But if it doesn't reach the edge, we got to store this new position. So else, we're going to store it. So we're going to say particles.poke. Remember, the first one is the value, so we'll poke the new value of x at the sample index at channel 0, because channel 0 is x. And I'll just write it once again. X. And let's do the same thing. We're going to store it for y at position channel 1. So y. Channel offset 1, I should say. Great. So now we've saved the new positions. And yeah. So if this is all correct, we're not making any sound yet, but we should be able to visualize these particles moving around. So let's try that. So let's move out of Gen codebox, and sorry, I'm just reviewing, making sure. This might have some mistakes, so let's find out when we come back. But let's see. So now we're gonna move out of Gen, and we're gonna create our opengl visualizer. So I don't really use jit.world, but you can. If you don't know about JitterGL, it's probably good, like any of these things, to just do an intro tutorial first. Alright, so what you need is a render with a context, and this is like what's gonna actually draw the shapes. And I'm not a GL expert, so any mistakes in terminology, I'm sorry. I'm gonna create a trigger for activating this, or maybe I'll just keep it always active with a load mass 1. Okay? And then we're gonna you got to use a Q metro, because you got to Q limit these. I'll run it at a rate of 40 milliseconds. So every 40 milliseconds, we're gonna redraw this context. And how to do that? I'm sorry, I'm writing some stuff. I'll explain later. So we're gonna do 3 things each time. The first thing we're gonna do is erase whatever was there before, so that it doesn't just bleed. And then when you send a bang to it, it draws it. The output I'll describe in a second. That's going to be for something else. Now let's create a little window to view this all. We'll do jit.p window. And then I'll do @name C, because that's our context. So it matches C. So in this little window, we're going to see everything happen once it's set up. Okay, now we're going to need another thing. So here's how we're going to access, or okay, before I do that, okay, so I just sent the load mess one in now. So now it's drawing, but there's nothing to draw, so it's blank. Okay, so how we're gonna visualize this, and you can visualize it in many ways, but we're gonna use jitgl.gridShape, and there's the grid shape. We're gonna make it a circle instead of a sphere because it's not 3D. It won't look any different right now. Let's scale it down 0.05 because yeah, we're gonna want it smaller for having 8 particles moving around. I also want to give the context name, although I don't know if you really need it. All right, another argument we need is the name of this, and the name is going to be particle. Okay, I think that's all we need. Well, I guess we can give it a color. GL color, so 1111, and let's give it some transparency. So that's just an RGB with the 70% transparency. Oh, it won't be transparent because we need some more arguments. I can't remember what they are. I think they're blend and depth enable. Let's just forget about it. It doesn't matter. Okay, so we have a particle. All right. All right. So, but obviously we don't want to just show one particle. So we actually want to use a multiple, which is called gl.multiple, and this will allow you to create multiple instances of a certain GL object. And we're going to draw it to our context, which is C, and we're going to give it a target name, which is going to be the name of our object below, which is called particle. So our target name is particle. Oh, before that, I'm going to put a 1, because we're only going to affect one parameter of it, which is the position. And there's another argument we need, GL parameters, called position. So this is also stuff you might want to look into on your own as a basic tutorial, but for a more basic understanding. But essentially we have this grid shape, which is this circle, and then this multiple will create multiples of the circle. How many it creates depends on the matrix you send in here, and if I hover here it says position array. So we got to send it a matrix of positions, and if we sent it, so a position is x and y and z. For this case we only need x and y, and that's going to be a 2-plane matrix. You'll have to look that up if you don't understand. That just means there's 2 values stored in each cell of the matrix, and those 2 values will be the x and y position. And so if we sent it, depending on how many cells of the 2-plane matrix, it'll create that many of these circles. Now, how come we see 1 here? That's because you have to give it this automatic 0 argument. Ugh, why didn't that work? Oh, I guess it does 1 by default. But generally this will help to prevent this one from just drawing a single shape that's separate than the multiples. Okay, so we have this kind of set up. Now we just got to feed in a position vector. And in fact, let's see if this thing's working right. So I'm going to reset this, and let's open the buffer and take a look. And yeah, look, it's moving around. I don't know why there's more than 8. Okay, there we go. I just forgot to send in this number. So okay, now it's sized to 8, and yeah, if I move this, we can see that the particles are moving around. This is the x position, this is the y position, this is the velocity x, and this is the velocity y. So yeah, that's working, I think, and now we just need to visualize it here. So now comes in the time to once again access the buffer, and to do that in the matrices, we can use jit.buffer. Now, it works very similar to the other buffer object. We got to put in the name, so we just have to match these names. Now, one important thing is that you actually have to match the number of channels in the argument. that will cause you issues if you don't. You'll keep being like, why does my buffer have only one channel? So we actually have to match those a bit. And this is just to match those so that it creates 4 channels, and it's working well. Sorry, audio. Okay, sorry, audio dropout. Now, we want to send in another message into here, which is to tell it how many indexes to output. I don't know the correct term for that. And the argument that we'll use is this output last. So we'll do pack output last I. So this is going to tell it how many indexes or cells to output. And we're going to use 8, but it's actually starting at 0, so we're going to minus it by 1 to 7. And yeah, so that means it'll go from 0 to 7, which gives us 8 particles. So that's the output last thing. Sorry, I don't know. I'll make it neater as we go on. Okay, and then we have to actually output the matrix, and that's using this output thing. So every frame, it's going to erase this, and then it's going to output the matrix, and then it's going to draw it. So right now it should be outputting it. Let's check that up with jit.cellblock, and here we can see it's outputting the values. Now we don't need all 4 of these. We just need the position. We don't need the 2 velocities. So I'm going to first unpack 4. That's just going to unpack the 4 planes. Now, yeah, if you use this, each channel becomes a plane. And we only need 2 planes, like I said before, for the X and Y. So we'll just jit.pack 2. So we'll just get the first 2. And let's just see that. Great. And now let's send it to here. Okay, great. It's working. But why are they so small and also fast? Okay, well, they're small because we scaled the size of these to 0.05. So that means that the box of -1 to 1 is actually just like this big, you know? So we actually have to make the we have to scale up the X and Y positions to make up for that. Now, since we scaled it to 0.05, we're going to have to do the inverse of that, which is 1 divided by 0.05, which is 20. So we're going to have to scale it up 20 times. So I'm going to use jit.expr to do that. And I only do this because it just helps, since it's a float 32 data type, that you can do this without giving it additional arguments. So I'm just going to multiply it by 20. That's all this is doing. I'm just multiplying the positions X and Y by 20. And yeah, now see, it's flying. Now it's going pretty fast. Okay, sorry, I figured out what was wrong. So way back when we made this initialize thing, I forgot to set init to 1 so that we knew it was finished. So at the end of initializing, you set it to 1 so it doesn't keep calling it, and it was calling this over and over. So yeah, now we can see it. And yeah, they're moving correctly. We can look in the buffer, and it looks a lot less chaotic now. And yeah, they're moving fine, and everything looks good.